Hi, everyone. I'm Mariem Magdy. I'm a third-year PhD student at Queen Mary University of London. So today I will be talking about the asymptotic charges for spin-1 and spin-2 field on Minkowski spacetime. So this work is in collaboration with my supervisor, Juan. So first, I will give a brief introduction of the work I'm presenting today. So talking about asymptotic symmetry, I have to briefly mention this diagram. This is known as the infrared triangle. At each corner, we have one of the key subjects of research in physics, including soft theorems and the gravitational memory effects. And we now know that these different topics are linked. And in the case of asymptotic symmetry, which is a subject which is more theoretical in nature, the relation with the gravitational memory effects make the study of asymptotic symmetry more interesting because of the observational implications. So when we study asymptotic symmetry, one can study the symmetries of spacetime at either null or spatial infinity. At null infinity, we know that the asymptotic symmetry group for asymptotically simple spacetime is given by the BMS group, which is an infinite dimensional group. And at spatial infinity, the study of asymptotic symmetry have been more challenging, mainly because of the singular nature of spatial infinity when we compactify spacetimes with non-vanishing ADM mass. So still there is a lot of research on this topic. And we also now know that we have an infinite dimensional symmetry group also at spatial infinity. So one of the interesting problems when we consider asymptotic symmetry is the link between asymptotic symmetry, asymptotic symmetries defined at future and past null infinity. So from Minkowski spacetime, let's say we have a charge Q, which is defined on scri plus and also on scri minus. We can take the limit of these charges as one approaches spatial infinity. And the problem of the link between these charges, or the limits between for these charges, is called the matching problem. So this problem has been studied by different research groups. And as I mentioned in our work, what we aim to study is the asymptotic symmetry in Minkowski spacetime. And we also study the link of the charges defined on scri plus and scri minus. However, it will become clear later in my talk that we do not make any assumptions about antibodal identification to get this matching between the charges. And we also look at the problem of asymptotic symmetries in the context of an initial value problem. So this is one of the key things that differentiate what we do from other research groups. So in our work, we make use of Friedreichs formulations of spatial infinity. We know that in the standard conformal compactification of Minkowski, we have spatial infinity represented as a point on the conformal diagram. In Friedreich formulation, spatial infinity is blown up to a cylinder. And we see this in this three-dimensional diagram here, where we see that the cylinder I connects the past null infinity with the future null infinity. So the details of obtaining this representation in Minkowski is not a very interesting for the talk. However, if we start from Minkowski spacetime with the physical coordinates, then if we apply some coordinate transformation as well as a conformal transformation, then we obtain a conformal metric written in terms of the coordinates tau and rho. And these are what we call the Friedreichs coordinate. And in this metric, we have that the cylinder representation of spatial infinity. So in this specific representation of the cylinder, it's called the horizontal representation because what we have is that we have past and future null infinity are represented as constant tau on this two-dimensional diagram. And if we look at the conformal metric, we can introduce different sets of the unphysical spacetime. So we have the cylinder I, and we also have the critical sets at which past and future null infinity meets the cylinder. And also, since our aim is to express the charges of the critical sets in terms of initial data on a Cauchy hypersurface, so if we have this initial hypersurface S, this initial hypersurface intersects the cylinder at this I0. So the techniques that we use in our work are mainly related to two papers. One, which is by Friedreich and Kanner, in which the expression for the Newman-Penrose constant in terms of initial data is obtained, and also a paper by my supervisor Juan and Edgar Gasperin, in which they analyze the Newman-Penrose constants at the critical sets for spin-1 and spin-2 field, and they show that there's no natural correspondence between the Newman-Penrose constant at past and future null infinity, unless the initial data are chosen to be time symmetric. So for the rest of the talk, I will be giving a brief discussion of how we obtained the results. Because of time restriction, I will only consider the spin-1 case. And then I will also discuss the main results for both the spin-1 and spin-2 cases at the end of the talk. Generally, the expression for the asymptotic charges are given in terms of quantity, written in terms of the Newman-Penrose gauge. So we have quantities, or the field are written in terms of these frames, which are adapted to null infinity, and they satisfy the Newman-Penrose gauge condition. However, the frames which are more adapted to Friedreichs formulation of spatial infinity are frames which are adapted to conformal geodesics and Cauchy hypersurface. So the first step in finding the expression for the charges in terms of initial data is to transform the expression from the Newman-Penrose gauge to the F gauge. So the transformation between the frames which are satisfy the Newman-Penrose condition and the F gauge frames are given in the general settings in the paper by Friedreich and Kanner. However, for our work, the explicit transformation in the case of Minkowski is also given in the paper by Juan and Edgar. So if we make use of this, we can obtain the expression for the charges in the F gauge. Now, to analyze the charges specifically for the spin-1 field, we work in spinorial notation. So we have that the spin-1 field is expressed by symmetric valence to space spinner that satisfy this wave equation. Then if we contract the spinner with the F gauge frame, what we get is we get three components, phi0 and phi1 and phi2. We can write these components at first order in terms of spin-weighted spherical harmonics. And then we have higher order terms that vanishes at the cylinder at rho equal 0. So now making use of this expansion and the equation and assuming generic boosted initial data that are consistent with the field expansion, we find that the solution for the coefficient A1 diverges logarithmically at tau equal plus or minus 1. So these are at the critical sets. At past and future null infinity. So then if we restrict our data set by applying certain regularity condition, we find that the solution for A1 is written in terms of Legendre polynomial with a constant that depends on L and M. So then in our work, we're only interested in super translation charges. These are associated with smooth functions on S2. And for simplification, we can write these in terms of spherical harmonics. Then if we assume initial data that satisfy regularity condition, we get first result, which that our charges at I plus and I minus are proportional to the initial data that we have. So we have to the A1 bar at tau equal plus or minus 1. And then we also get that the charge at I plus is equal to the charge at I minus multiplied by this factor minus 1 to the power of L.
2 minutes.
Yeah. Finally, just to summarize, the main result of our article is given by this theorem. So we have that for generic boosted initial data set, the asymptotic charges at the critical sets are well defined if and only if the freely specifiable data satisfy certain regularity condition. And for a given harmonic, the charges are expressed in terms of the freely specifiable initial data, and we have a natural correspondence between the charges at I plus and I minus. So the last thing I want to say is that in this paper, we focused on Minkowski spacetime to look for the spin-1 and spin-2 field asymptotic charges. So this served as a prototype for our next research project, which we're trying to analyze the charges in the full gravity setting in the context of an initial value problem using Friedreichs formulation of spatial infinity. So this will be work in collaboration with, again, my supervisor, Juan, and also one of our collaborators in the US, Kartik Prabhu. So this will be the end of my talk. Thank you for listening.
Very well timed. Thank you very much. So do we have any questions? I'll give people a moment to write things. In doing so, I was wondering, could you say a little bit more about these regularity conditions? I don't know if they're too technical to go into.
I think it's not too technical. It's more, I guess, very interesting. It's more the conditions that we have are more on the coefficients that we have. So we have some conditions that, for example, some of the coefficients have to be vanishing. So we have the Friedreichs possible have to be vanishing, and also some of them has to be, I guess, equal to other orders in the coefficient. So that's the main thing that we have. It's just more on the coefficient of the expansion that we have. So that's it. And since we're using freely specifiable data, so we technically can specify these data as much as we want. So we're free to set the data how we want it to be. So.
Cool, thank you. Okay, no questions currently in the either the chat or the Q&A by the looks of it. So I think everything was covered very well, or people are a bit shy, in which case I hope they can ask their questions on Slack. So thank you very much, Mariem.